I want you to imagine the sensation of gliding across a landscape at 300 kilometers per hour. In the early 1990s, this was the promise of the high-speed rail network in Germany. It was a marvel of efficiency, but there was a subtle problem that bothered the engineers: the noise. When a solid steel wheel rolls over a steel rail at those speeds, the vibrations are intense. It creates a high-pitched drone that permeates the cabin, vibrating through the floorboards and into the seats. To solve this, designers looked toward a solution used in slower city trams: the resilient wheel. This wasn't a single block of forged steel. Instead, it was a composite assembly. You had a central steel hub, a series of rubber damping inserts, and then an outer steel tire wrapped around the outside. The idea was simple and elegant. The rubber would absorb the high-frequency vibrations, making the journey whisper quiet for the passengers. It was a triumph of comfort, but it introduced a mechanical complexity that the industry had never faced at these specific speeds and loads. When we look at a wheel, we see a rigid object. But in the world of materials science, everything is flexible. As that composite wheel rotated, the outer steel tire would slightly deform at the point of contact with the rail. Because it was sitting on soft rubber rather than solid steel, it could flex much more than a traditional wheel. This flexing is what we call cyclic loading. Every rotation of the wheel, thousands of times per minute, caused the steel tire to bend and then spring back. In the engineering world, this is the perfect recipe for fatigue. The evidence points toward a fundamental misunderstanding of how these thin steel tires would behave as they wore down over time. In a solid wheel, you can run the material down significantly because the core remains supported. But in a resilient wheel, the thinner the outer tire becomes, the more it flexes. As it flexes, tiny microscopic cracks begin to form on the inner surface of the tire, the side facing the rubber, where no visual inspection could ever reach. We often think of metal as something that fails suddenly, but fatigue is a slow, patient process. It is the steady propagation of a crack, 1 micron at a time, until the remaining material can no longer support the load. In the case of the high-speed line, the tire thickness was monitored, but the limit was based on the standards for solid wheels, not for this specific composite design. The stresses were being concentrated in a way that the original models hadn't fully accounted for. The geometry of the tire changed as it moved, turning the circle into a slight oval with every revolution. This constant pulsing eventually reached a critical point. The missing angle in many discussions about this topic is the role of the rubber itself. While it provided comfort, it also acted as a thermal insulator. The heat generated by the constant flexing of the steel had nowhere to go, potentially altering the material properties of the tire over years of service. On a quiet morning in June 1998, one of these tires finally reached its limit. It didn't just wear out, it suffered a complete structural separation. The tire transitioned from a ring to a strip of metal, which then caught on the track infrastructure. This single component failure led to one of the most significant engineering investigations in history. The lesson here is about the hidden costs of optimization. We optimized for noise and passenger comfort, but in doing so, we moved the failure point from a visible area to an invisible one. We traded a simple, well-understood system for a complex, interdependent one. The evidence boundary shows us that even the most successful designs have a limit, and those limits are often found where two different materials, like steel and rubber, are forced to work as one under extreme pressure. Today, high-speed lines have largely returned to monolithic forged steel wheels. We have accepted a bit more noise in exchange for a component whose fatigue life is predictable and easily monitored. It is a reminder that in engineering, every benefit comes with a trade-off, and sometimes the most resilient designs are the ones that remain the simplest. If you find these deep dives into the mechanics of history valuable, please consider following for more case files. Let me know in the comments what component you think we should analyze next.